Hi everyone, my name is Keith. I'm from Harry Ward University, Malaysia, and I'm a Year 1 Actuarial Science student.
Hi, I'm Christian and I'm from Year 1 Mechanical Engineering.
Today we'll be presenting about differentiation. Now we'll start with the basics of differentiation. So we have an equation, y equals to a times x to the power of n. So how do we differentiate this? To find the differentiation, we take n times a times x to the power of n minus 1. There's two examples here. Firstly, y equals to 7x to the power of 3. So to find dy dx, we take 7 times 3 times x to the power of 3 minus 1, following the formula shown, which gives you an answer of 21x squared. The second example, we have y equals to x power 5. So dy dx equals to 5 times 1 times x to the power of 5 minus 1, giving you 5x to the power of 4. Now we will look at a common problem, which is differentiating trigonometric functions. So there will be three cases here. Firstly, y equals to a sine bx. dy dx is given by a times the differentiation of the sine function times the differentiation of bx itself. So dy dx is shown by a times cos bx times b, which gives you an answer of ab cos bx. Next, y equals to a cos bx. So the differentiation is similar to the sine one. It's a times the differentiation of the cos function times the differentiation of bx itself, which gives you dy dx equals to a times negative sine bx times b, which gives you a final answer of negative ab sine bx. Lastly, we have y equals to a tangent bx. So dy dx is given by a times the differentiation of the tangent function times the differentiation of bx itself, giving you dy dx equals to a times secant square bx times b, giving you a final answer of ab secant square bx. Now we'll proceed to the two examples here. So to start, we have y equals to 2 sine 4x. So we're just going to follow the formulas we used at the previous slide. So dy dx is 2 times the differentiation of the sine 4x function times the differentiation of 4x itself, which gives you 2 times cos 4x times 4, giving you a final answer of 8 cos 4x. The second example, we have y equals to 5 tangent 3x to the power of 5. So dy dx is 5 times the differentiation of the tangent function times the differentiation of 3x to the power of 5. So combining everything will give you an answer of 75 x to the power of 4 times secant squared 3x to the power of 5. Proceeding, we'll look at the differentials of exponential and log functions. So let's begin with log functions. Y equals to ln ax. So dy dx equals to 1 over ax times the differentiation of ax itself. So dy dx is basically a over ax. When you cancel the a's out, it gives you 1 over x. Next, we'll look at exponential functions. Exponential functions are simple to differentiate, which will be d over dx of the power times the original function itself, which gives you dy dx equals to a times e to the power of ax. So the examples are, firstly, y equals to 2 ln 3x. So dy dx is 2 times 1 over 3x times the differentiation of 3x itself, which gives you, after simplification, 2 over x. The second equation, you have y equals to e to the power of 3x squared. So dy dx equals to the differentiation of 3x squared times the original function itself, giving you a final answer of 6x e to the power of 3x squared. Now we'll look at composite functions. Composite functions make it easier to solve regular differentiation problems based on the information given in the question. We firstly consider the formula, which is very important in this case. Dy dx equals to dy du times du dx. So now we'll look at the example shown. Y equals to 2 over x squared minus 3x plus 1, which looks difficult to differentiate. So we can let u equals to x squared minus 3x plus 1. So now we'll start. To find dy dx, firstly, we need to find y in terms of u to find dy du. So we know that y equals to 2 over u after substitution. So we know that dy du is a differentiation of 2 to the power of u minus 1. Following the same steps shown in the first slide, basically you get a final answer of negative 2 over u squared. So now we know that u equals to x squared minus 3x plus 1 as well. So du dx is basically 2x minus 3. So dy dx, following the formula shown above, is negative 2 over u squared times 2x minus 3. So after substituting back what u is, so u is basically x squared minus 3x plus 1. We put that back into the equation there, and then we can simplify it to show a final answer of negative 2 times 2x minus 3 over x squared minus 3x plus 1, and the whole thing is squared. Next, we'll look at the chain rule. The chain rule is basically used when you have an equation with a very high power. So y equals to ax plus b to the power of n. So dy dx equals to n times ax plus b to the power of n minus 1 times the differentiation of ax plus b, which is inside the brackets. So you get dy dx is n times ax plus b to the power n minus 1 times a itself, giving you a final answer of an times ax plus b to the power n minus 1. So now we'll look at an example for this kind of questions. Y equals to 5x plus 2 to the power of 4. It doesn't make sense to expand this, so we can use the chain rule. So basically, we bring the power down. We have 4 times 5x to the power of 2, 5x plus 2 to the power of 4 minus 1, which is 3, times the differentiation of 5x plus 2, giving you a final answer of 20 5x plus 2 to the power of 3. So now we have the product rule. The product rule is basically when there's two functions multiplied together. So in this case, we know that there's two functions of x multiplied together. So dy dx is basically du dx times v plus u times dv dx. So we have an example here. Y equals to x cubed times 5x minus 1. So y equals to x cubed times 5x minus 1. Yeah. So u equals to x cubed. Du dx equals to 3x squared. So we find that first. Then we know that v equals to 5x minus 1. Dv dx equals to 5. So dy dx, following the formula shown, is 3x squared, which is du dx, times 5x minus 1, which is the original function of v, plus the original function of u, which is x cubed, times the differentiation of the v function, which is 5. When you simplify, you get a final answer of 20x cubed minus 3x squared. Next, we will look at the quotient rule. The quotient rule is done when one function is divided by another. In this case shown, one function of x is divided by another function of x. So the formula to find dy dx goes by du dx times v minus u times dv dx over v squared. So the equation on the top normally takes u, while the equation at the denominator takes v. So in our example, we have y equals to x squared plus 2 over 3x squared plus 2x plus 1. So u equals to x squared plus 2. Du dx is given by 2x after differentiating. V is 3x squared plus 2x plus 1. So your dv dx is 6x plus 2. So following the formula, we can find dy dx. So we have du dx, which is 2x, times 3x squared plus 2x plus 1, which is the original function of v, as shown in the formula, minus x squared plus 2, which is the original function of u, times the differentiation of the v function over the v function squared, which is 3x squared plus 2x plus 1. And after simplifying this, depending on how the question asks you to, you can get a final answer of 2 times x squared minus 5x minus 2 over 3x squared plus 2x plus 1 squared, the whole thing squared. Now I'll pass it to Christian.
Next, we will learn how to find the tangent and normal equations of a curve. Starting with the tangent equation, the first step is to differentiate the given equation. The second step will be to substitute the known x coordinates into the differentiated equation to obtain the gradient of the tangent. The final step will be to substitute the gradient as well as x and y coordinates into the straight line equation shown in step 3. Instead of this equation, y equals mx plus c can also be used. To find the equation of a normal, the steps are very similar. The only difference is that there is an extra step, which is to use the negative reciprocal to find the gradient of the normal. Here is an example to try by following the steps previously mentioned. We start by differentiating the equation of curve. In this case, we only need to apply the chain rule to differentiate it. This results in the differentiated equation to be -6 multiplied by 3 minus 2x squared. After this, we substitute x as half to get dy over dx to be -24. This is also the gradient of the tangent. Finally, we sub the coordinate values into the equation of a straight line to obtain the equation of tangent, which ends up to be y equals -24x plus 20. Next, we need to find the normal equation. Since we already have the gradient of tangent, we can use the negative reciprocal to obtain the gradient of the normal, which in this case is 1 over 24. Just like before, we sub the gradient and coordinates into the straight line equation. Therefore, we obtain the equation of normal to be y equals 1 over 24x plus 383 over 48. Now we will learn about stationary points. Stationary points are a point in the curve where the gradient will be parallel to the x-axis. Hence, at stationary points, dy over dx will be equals to 0. Stationary points have two natures, maximum and minimum. They are considered to be minimum when the second derivative is more than 0 and maximum when the second derivative is less than 0. Now we can try an example equation, starting by differentiating the equation of curve. Using simple differentiation, we obtain dy dx to be 3x squared plus 6x. Next, we equate this to 0 and factorize it to get the x coordinates of the stationary point, which are 0 and -2 for this curve. The last step is to find their natures. We first need to find the second derivative, which is obtained by differentiating the equation of curve twice. This gives us 6s plus 6. Lastly, we sub both coordinates in. Since subbing x equals -2 gives us a second derivative less than 0, that means that there is a maximum point at x equals -2. And since subbing x equals 0 gives us an answer more than 0, that means that the minimum point is at x equals 0. Rate of change. Rate of change is the derivative of a variable in terms of x. The formula shown here on the left is very important to solve rate of change problems. The volume of sphere is increasing at a rate of 25 cm³ per second. Find rate of change of the surface area when radius is 2.5 cm. From this question, we know that dv over dt is equal to 25 and r is equal to 2.5. We start by differentiating the formula for the volume of sphere in terms of r. Note that this is also the formula for surface area. Bringing down the power tree and subtracting the power by 1 gives us 4 pi r. Subbing r equals 2.5 gives us a surface area of 25 pi. Now we use the rate of change formula from the left-hand side, but in terms of volume. Subbing the values we got in the formula, we get the rate of change of radius to be 1 over pi. Next, we find the second derivative of v, which is 8 pi r. This gives us 20 pi after subbing r as 2.5. We finally apply the formula of rate of change for surface area. Subbing in our known values gives us the rate of change of surface area to be 20 cm³ over time. The last topic in differentiation is small change. If y is equal to a function of x and there is a small change in x, the small change in y will be represented by the product of the first derivative of the function and the small change of x. Let's practice with this example. Y equals 3x squared plus 4. Given that x is increasing at the rate of 2 units per second, find the rate of increase in y when x is equal to 2. After reading this question, we know that the small change of x is 2. Differentiating the y gives us 6x. This is because differentiating a constant gives us 0. In this case, the constant is 4. Subbing x equals 2 into dy dx equation gives us dy dx to be equal to 12. Applying the small change formula results in the small change of y to be 24. That's the end of this video. We hope you learned something and please remember to like and subscribe. All the best for your exams.